Welcome back, Professor Caps. This week was magnetic fluid, which seemed like a really cool project to do. And we got ours to work, asterisks, but we'll get into why I didn't get the full Monty, or at least why I think I didn't get the full Monty. The video is really cool. Got to watch. Anyways, so what we're dealing with, or what the project was to mix LaserJet toner with oil. They use pure vegetable oil. Excuse me, allergies. The idea is that the iron oxide in the toner is magnetic, and that by putting it in oil, it allows the magnetic particles to become fluid. And to some degree, we got it to work. Gotta be real careful with this jar, dude. It is like my kitchen table will remember this experiment forever. Shouldn't have done it there. Such is life sometimes. So that was the assignment that we were doing. That's what we were trying to achieve. And we got somewhat there. We'll take a look at some of the videos and I'll go through a conclusion. But the science behind what we're trying to do, in order for one of these transition metals to be magnetic, the d orbitals need to have electrons but not be full. So I did a little diagram here to kind of show what we're dealing with. This is an example of what a paramagnetic set of d orbitals might look like, a valence shell. So each one of these has one electron. Each electron's got a negative charge, making the metal negatively charged, making it magnetic. Whereas in a diamagnetic, all of our d orbitals are completely full. So the charges are balanced. There shouldn't be much charge on this. Now, to kind of better explain this and why this is how it is, keep in mind these are all pretty big generalizations, and there's always going to be exceptions. But basically, with a high spin, you have a lower splitting energy. And with a high spin and a lower splitting energy, all 5 of the orbitals will remain closer together, and it will take less energy to fill each one of those orbitals. And the way it goes is that each orbital wants to have, this is the analogy I heard and I liked, each orbital wants to have its own bus seat. It doesn't want to sit with anybody else. So as long as the energy is not too bad, it's going to keep going one per seat or one per orbital. So high spin means that we get our electrons spread out, and that's because we have a lower splitting energy. And with our electrons split out, we generally have a higher magnetism. Generally, not always the case. If the orbitals are full, it doesn't matter what the splitting energy, high spin, low spin, because they're full. And the opposite side of that, we have a low spin, which means that we have a higher splitting energy. So a higher splitting energy means that our D, in the case of an octagonal, in the case of a normal situation where we have the metal and 6 ligands, it's a octahedral. Woo, got there. Octahedral shape. The dz squared and the dx squared minus y squared orbitals are butted up right against the hot points where the ligands will join, and so there's a higher charge on those orbitals. Takes higher energy to get electrons in there. So low spin, we have a higher splitting energy, which means it takes more energy to get the electrons into those orbitals, which means that the bottom shell, the bottom 3 orbitals, are going to fill up first before anything starts going to the top. So generally when our orbitals get fully filled, or at least partially filled, more fully filled, few partially filled when we have a low spin system, which generally can be magnetism being down. You can still have magnetic, still can happen. Say there's 3 electrons, boom, boom, boom. Then each one of the lower shells will only have one end and still have negative charge. These are all generalizations. So let's cut to some of the footage and see what we actually got. All right, so we are trying to find uh, our right saturation level between the olive oil, or not the olive oil, the canola oil, vegetable oil, and our toner. We're getting movement, but we're not getting the cool spikes. Anyways, let's keep going. All right, so we're getting closer. I'm using the magnet. I'm able to draw it out. All right, so we've got a little bit more thin. You can see my magnet running through it. I'm able to pull it out a little bit. I don't know if the issue is my magnet. It's starting to seep into the paper. You can definitely still see my magnet running through it. I don't know if it's my toner, my magnet, canola oil instead of vegetable oil. This is probably the best consistency that we've gotten yet so far. See it pulling along. All right, cool. Oh man, that was exciting. So much fun. So you can see the magnet passing through. You can see that there was some magnetic pull, but not a whole lot. I did some research on this afterwards, and what I found is that the oil type, so I thought it might have been an oil thing. It is not an oil thing. The oil that I had was fine. They suggest, in the video, obviously, gosh darn man, in the video, they use pure vegetable oil, but when I did my research, it showed that any of these like flowy oils, olive oil, canola oil, all of these oils work. That's not part of the equation. What is part of the equation is the toner that you use. So I ordered this on Monday because it was the only one that was like not really suspect, no name brand type stuff. What I think I got though is a toner that had like a low iron oxide or low metal oxide count. So we did get some magnetism. There were still some metal shaving shards in the toner, but it wasn't like a whole lot. So I think that's where our issue was. We still did get some magnetic pull. We still produced a metal liquid or a magnetic liquid, just not like the cool spiky boys that were in the other video. Just a thought, it might actually be pretty cool to show some of the more successful students, because I'd like to see that it's like a thing and not just some dude on TikTok is able to achieve. Anyways, so that's where I think our issues were. We did get a magnetic fluid, just not all that we were hoping for. Cool experiment all the same, and good principle. All right, thank you.